Okay, well, that was not a great start to the semester. Anyway, this will work. So what I wanted to do was to go through physics. Um, I was going to show you what was on the Canvas page for physics. So physics, the homework assignments are in a PDF file. So this is the first link. So again, this is something you're probably going to want to download. And yeah, that's another thing that's a problem here is that even Canvas is not working. So that's great. It's running very slowly. Let's try that again. Okay. So there's this PDF file with homework from the different chapters. And so, for example, the first chapter has 9 problems. And so you will do the homework as according to this file. Just like with calculus, there are videos for the homework. So this will give you a list of the solution videos, and this is where you upload your physics homework. So you'll use the Canvas app, which I realized I haven't done it for this class, explained it, so I need to do that. I mean, the governor's school students know how to do it, but for the physics students, I'll need to explain how that works. So that's where you turn in your homework and you'll take pictures of it. We'll be doing some in-class work. So these are the in-class handouts. These are, again, there'll be, in this case, there'll be a download. So chapter 1, we have one worksheet, significant figures. So we'll do that, and then you'll upload the completed assignment here. So there'll be places for you to upload your homework and also to upload in-class assignments. Now, if you are taking or want to take the calculus-based physics, the lectures are here and the homework assignments are in the University Physics book. And so we'll talk more about that later. You don't have any assignments coming up for a few weeks. The next thing is part of the labs will be you'll be given an electronics kit the first lab time that you have. And you'll take those home and you'll work on those projects. So let me just click on this. What I'm working on, I haven't completely got it set up yet, but I don't need to. I'm just getting it done as far as time goes along. So what you'll see right now is there are videos, and the videos have questions embedded in them, but they also have explanations of how to do the experiments or the labs associated with the electronics kits. They use what's called an Arduino, which is a microcontroller, and the kit comes with a lot of extra stuff as far as motors and resistors and diodes and LEDs and all these things you may never have heard of, but half of the lab experience will be in person and half of it will be at home, and you'll use these kits. You don't have to pay for them. They were paid for out of the CARES Act So you'll just be given those. There'll also be like a plastic shoebox, which will allow you to, it's always hard to get things back in their original package, so you'll be able to have a little more room to put the stuff that you're working on. So each one of these will have a quiz embedded in it, so I know that you're working on them. There'll also be cases where I'll make some kind of an assignment, like down here. It says Arduino Tutorial 3 circuit upload. So you will need to upload a circuit, a picture possibly. So there'll be assignments that go along with these. Like I said, this is a work in progress. Now, as part of the labs, you will need to install the software on a computer and hook up the Arduino through the USB cable to a computer. So if you have a home computer, you can use that. You don't have to use your governor's school laptop. If you don't have a home computer that you can use it on, you want to use the governor's school laptop, we will need to install the software. It doesn't have the software already installed. So please bring your laptops if you want to install it on your laptop to your first lab class. What we'll do there is we will find there's a certain identifier for each computer. I need to send you'll turn your computer on. I will send who has their computers turned on to the IT department, and then they will install the software remotely. And then once you go home, then you can plug it up and it'll work. Now in the videos, they'll show you how to do this if you had your own computer which didn't have any security locks on it like your governor's school laptop does. So if you plan on doing it on your home computer, and it works on both Macs and PCs. But again, if you are planning on using your governor's school laptop for that, please bring the computer. And once you get here, the first thing we'll do is we'll turn on the laptops and I'll show you how to get the information about which particular laptops are being needed to work on, and then I'll send that off, and then while we're doing the lab, hopefully we'll get that stuff installed, and then by the end of the lab, you'll have it installed and everything will be fine. There are also in-person labs. This is what we're going to be doing either this week or next week. So for example, the first in-person lab, it says Lab 1 Measurement Uncertainty. There's a video that I want you to watch before you come to the lab, which gives you a little bit of an introduction of what we're going to be doing. We're only going to be having an hour in the lab, so we have to use our time efficiently. I'm going to hand these out. I just put it here so that I'd have some place that I would know where it is for future reference. You'll have a data sheet which everyone will fill out, and you'll upload your filled out data sheet here. So you don't need to bring the data sheet, but you will have to take it home and upload it. And the lab will be explained in the video, so I'm not going to go into that. Let's just talk a little bit about the labs, how that's going to work. So the labs are in 404 Scott Hall. The doors are going to be opened at 7:45 a.m. and they're going to close at 8 a.m. So you need to make sure that you come in time. This is Group A, the early group. There's the first week Group A and there's the second week Group A. Then there's the second, in this case, the lab will run from 8 until 9 a.m. The second group, the doors will open at 9:15 a.m. and they'll close at 9:30 a.m. The lab will run from 9:30 till 10:30. Okay, so when you come in, when the doors are open, you'll come in, there's a lobby. So in the lobby, you will fill out a COVID health form. And it's basically going to ask you if you've been exposed to anybody with COVID, if you have any symptoms like COVID. You know, the bottom line is don't come to the lab if you're not feeling well or if you've been exposed to somebody who has tested positive for COVID. So you'll fill out the form, you'll give it to me, and then we'll go into the lab. There are 3 setups, and you work in a pair, but you'll stay apart from each other. So you're going to be at least 6 feet apart from each other. Also remember, masks are required. So if you need a break from the mask, you'll have to go out of the room. So we'll say masks are, well, actually masks are required because there could be other people in the room. So yeah, that's going to be a little bit of a question. It's only an hour, so hopefully we don't have any problems. But if we do, we'll deal with it at that particular point. But masks are required in the room. We really don't know, you know, I don't have a great feel for what the ventilation is in there, so we're going to take as much precautions as we can. There'll typically be one person that will be working with the computer, collecting the data using the software, and there will be one person running the lab. I have a lab set up myself, so I will demonstrate how to run the labs. The basic thing that we need to get done during the lab period is to get the data, and I'm hoping that we'll have time so that one person can take the lab, can run the experiment, the other takes data. We'll switch places, we'll wipe down the computer keyboard and anything that's been touched, and then we'll run the lab again. I can't guarantee that we'll have enough time, so we may only have enough time to have one person run the experiment and the other person run the computer. We'll see what happens. This is all new to everybody. So let me show you the lab schedule. So this was set up by Mr. Graham. Now, as far as who is partnering with whom, you can decide ahead of time what you want to do. I'm not going to force anybody to be a lab partner. So here's the first one. We have Caitlin, Giovanni, Michaelan, Eric, Mason, Ethan. So we'll have 3 partners there. That's at 8 o'clock this Wednesday. So you need to be there at 7:45, between 7:45 and 8 o'clock. Because we really need to have everything filled out and you in your lab positions by 8. Give us the best chance of getting things completed. So you'll leave at 9. The next group will come in at 9:15, between 9:15 and 9:30. They'll fill out their forms. There are 5 people in this lab: Savannah, Jeffrey, Keegan, Alexander, and Alex. So again, you can, if you want to group up, if you want to determine beforehand who your partner is, that's fine. There are 5 people, so I will be the other person's lab partner, the one who may not have already chosen a partner. The third group is Riley and the 3 regular Dabney students, if we keep all 3 of them. So you know who you are. So you'll come the second week at 8 o'clock. The next group is September 2nd at 9:30 to 10:30. So this looks like the Covington group plus Trevor. Is that right? I think so. Okay. again, you can choose your partner if you'd like to beforehand. So those are the lab groups. If you have any questions about the groupings, let me know. If you want to go ahead and if you pick a partner ahead of time, just let me know so I know what to expect. Okay, so that is the lab stuff. So I'll probably send out an email just reminding you that you need to watch the video before the lab. The next class that we'll have is on Friday, and hopefully by then they'll have this Zoom thing figured out. If not, we're in trouble. Okay, so there's in-person labs. The office hours are when you can arrange a time to talk to me via Zoom. So these are the two things. This is the link that you would have used today if it was working to get into the classroom. This is the Zoom link for office hours and also will be for taking the tests. And please take the COVID-19 awareness training before the lab on Wednesday so you know what the rules are for being on campus. You know, only the people taking labs are going to be on campus. Also, for attendance, after you've watched the video, send me an email to let me know you've watched the video for this particular class. I think that's it. Like I said, I will post this for the non-governor school students. I'll just show you where it is, what it'll look like. I've done this for calculus class because I have a online section of this, but what you'll have is something similar to this, but there'll be a video that says how to upload files to Canvas using the mobile app, and that's how you'll upload your homework assignments and your in-class assignments using this technique. So I will copy this over. Let me write it down so I don't forget to do it. So I'm just writing this down. Okay. So we're going to go ahead and get started on the material. Actually, I'm just going to, I've taught this class. It'll be the 10th year I've taught this class. And so what I'm going to do here is we're going to talk about Chapter 1. Now, Chapter 1 in the University of Physics book is a little more detailed. This is based more on Chapter 1 for the calculus, the old calculus-based book. But it has some introductory topics, and the ones that we're going to concentrate are on our measurements and sort of to go along with measurements are significant figures, and scientific notation. Now in the calculus-based physics book, they talk about vectors. And we could talk about vectors. We'll introduce vectors more in terms of this class. Actually, before we talk about the material, let me just give you a little background on calculus-based versus algebra-based physics so you have something to talk about or think about. So if you're an engineer or a physics major, you'll take calculus-based physics. If you're going into medical school or any medical field, you'll only need to have algebra-based physics. I've had some people who went to medical school who took calculus-based physics, but they really didn't need to. So the only people that should really consider taking calculus-based physics are people who are going to become engineers. Now, there are a couple of courses that are kind of like known to be gateway classes, and you actually take one of them. One is calculus. And we'll talk about this in calculus. But, some people may say, okay, you've taken calculus in high school. Even if it is doing wrong, you should retake it. And anyway, we'll talk about that in calculus. But in physics, everybody's going to have to take this calculus-based physics, which is it's kind of like a gatekeeper class. It's probably harder than it needs to be. And you'll find out that in physics, about at least 90% of the material is the same between algebra-based and calculus-based. So for an extra 10% work, you can get work now is you're going to save having to go over 90% of the same material again. So it might be worth the effort now to get it done. I mean, there is something to say for having taken a class twice or seeing the material twice by two different professors. They may emphasize something differently. So I'm not saying that it's a complete waste of time having to take calculus-based physics again if you've already taken algebra-based physics. But you can put some extra work in now, and that'll make it so that your course load will be lower later. Now, we'll actually be doing some, even in a regular class, we'll be doing a little bit of calculus, because 95% of the people in the class are taking calculus, so we don't want to waste that opportunity. It won't be as intense, and that's why there's the additional material for the calculus-based portion of the class. So you don't have to decide immediately, because we have to cover enough material in calculus to actually do the calculus-based part. So I guess you can see how calculus goes, how things are going this semester. If you decide if you want to change, you can do that, but it's not something you need to decide immediately in either situation. Okay. So the other thing we talk about is units. Because that kind of goes with measurements, significant figures. Okay, so let's talk about units first. A lot of this you've had before. In chemistry, you've dealt with units, and there are similar ones, but the main three units that are used, at least in the first semester of physics, are ones for mass, and in physics, the unit of mass is a kilogram, not a gram. Chemistry, you use grams as the basic unit. We use kilograms. It's just that in terms of what you're dealing with, things tend to be more likely to be a kilogram than to be a gram. So if you did everything in grams, you'd end up with a lot, 1,000 times bigger numbers. Okay, so mass is one of the units. The next one is length. The unit of length is a meter. Now, let's go here. The abbreviation for kilogram is kg. The abbreviation for meters is m. The third unit is time, and that is in seconds. And we just use an S for that. So those are the basic units. There's in the second semester we'll be dealing with electrical charge, which is coulombs. What else do we have? But even coulombs nowadays, you can work back to these three main units. So things like, we'll talk about newtons later. Newtons are derived unit. So Newton is a kilogram meter per second squared. So you can see it's based on these three basic units. Velocity, which we'll introduce shortly, as units of meters per second. Sometimes units we just keep in the base units like meters per second. Sometimes we define a new unit like newtons to replace this. So a newton is 1 kilogram meter per second squared, but we don't talk about newton. We don't talk about force. This is a unit of force. We don't talk about units of force as kilogram meters per second squared. We talk about it in newtons. And then maybe if we need to do some dimensional analysis, we may rewrite it as a kilogram meter per second squared, but we'll normally call it a newton. Now, all of these units have a definition now that is based on not on a standard, like it used to be a meter was this piece of material in France at a certain temperature, and that was the standard. It's actual physical quantity, just like a kilogram used to be an actual physical piece of material. But nowadays, these are defined alternatively using things like the frequency of oscillation of a certain molecule. The length is how many wavelengths of light at a certain frequency. So these have fairly complicated definitions. In terms of things that we know, a meter is about a little bit over 3 feet, a little bit over a yard. A kilogram is 2.2 pounds. So just to give you an idea of the order of magnitude of these units. Okay, so I think that's all. If you're interested, you can go to Wikipedia and search mass, length, time, or kilograms, meters, and seconds, and find out all the details in terms of how they're defined at this particular point in time. Okay, let's talk about significant figures. This is what our lab will be addressing. And really what significant figures is doing is addressing measurement accuracy. Accuracy. There's that saying that if you can't measure it, you can't do anything about it. So that's one reason why we're doing all these tests, COVID tests, is if you don't know how many people are sick or who's sick, you can't really address the issue. And, there are, depending upon history, the ways of measuring quantities has gotten better over the years. A foot used a yard, well, not a yardstick, what do you call that? Anyway, you have a piece of wood or metal that has marks on it, and you can measure length that way. And, that accuracy of that particular measurement is dependent upon the accuracy of the thing that you're using as a base to measure. Sometimes it's based upon the diligence of the person taking the measurement. And in physics, to be able to specify the accuracy, instead of saying something like the length is equal to 1 meter plus or minus 0.1 meters, which is what you may have done in statistics. This could be 1 meter plus or minus 2 standard deviations of the mean of this type of measurement, whatever technique we're using. So rather than using this plus or minus terminology, what we do is we show the accuracy of a measurement by the number of significant figures that the quantity has. So let's give you an example. Let's say the mass is equal to 1.0 kilograms. And we could say that's versus the mass is equal to 1.01 kilograms. So this mass has more accuracy than this mass. And we show that by the number of digits. So this one would have 2 significant figures. This one would have 3 significant figures. This one would have 1 significant figure. So decimals and zeros and where the zeros are relative to decimals have an impact on significant figures. So the first thing you need to do is, I guess, know how do numbers represent different significant figures. It really doesn't matter what the measurement is, what the thing we're measuring. It matters on how many numbers there are. So, but these significant figures are given in a problem. We don't have to determine how many significant figures there are. The problem would state the mass is 1.01 kilograms, and we'd say, oh, that's 3 significant figures. That means the answer, after I do the calculations, the answer is going to be dependent upon the accuracy of the individual parts of the calculation. So we have to make sure that in doing our calculations, that we reflect the correct accuracy of the result based upon the accuracy of what went into that result. So let's just write a few numbers out and just talk about how many significant figures there are with each number. Okay, so let's just start off here. So this has 2 significant figures. Now the number of significant figures is not always the number of digits that are shown. Okay, so this is 2, and I'm going to use SF for significant figures. This one has 3 significant figures. This one also has 3 significant figures. So those are all easy. This is 0. Sometimes a 0 is a significant figure, and sometimes it isn't. So you basically look at the number and look at the rightmost element. And if that rightmost element or number is non-zero, which in this case it's 1, which is non-zero, then all the numbers to the left are considered to be significant. Now here, this one has only 1 significant figure, because we have these zeros, but the zeros are there to show that it's 100. If I didn't have the 0, if I left this 0 out, it would be the number 10. So to make it the number 100, I have to put a 0 there. But by not having a decimal point, I can only say that this number is significant. These are used for place settings. Now if I did 100 point, put a decimal point there, that would now become 3 significant figures. By putting that decimal point there, I have said that these zeros are significant. So it's a more accurate result. If I did 100.0, that would be 4 significant figures. Now if I do 10,100, this 0 is significant because it's between 2 non-zero numbers. But these zeros are not significant. Those are place settings to make it 10,100. Without those zeros, it would be 101. So this one has 3 significant figures. Okay, let's think about something else. Let's say you have 0.100. Now, you may think, okay, is that 1 significant figure? Because I've got these 2 zeros in here. These zeros here didn't count as significant figures. But If you are to the right of a decimal point, then the zeros do count. So let's look at these three, which represent the same number. If you put these in a calculator, it's going to be the same number. This one is going to be 3 significant figures. This one's going to be 2 significant figures, and this will be 1 significant figure. So this is a more accurate, by adding these extra zeros, we're saying that the number is more accurate. The measurement is more accurate. We're more certain of the value. I need to get rid of that page because I keep... Okay. Let's look at another one. So, if you have 0.375, 3 significant figures, 0.4600, that's 4 significant figures. Now, one thing you can do is if you put something in scientific notation, you can be more sure of significance. So let's say we have this one, 10,100. One way of writing this in terms of scientific notation would be 1.01 times 10 to the third. To the third, or is that to the fourth? To the fourth. Okay, so that's scientific notation because you have 1, 2, 3, 4. So if you move the decimal point 4 points, then you can make that the exponent. So I could show this as 1.010 times 10 to the fourth. I could show it as 1.0100 times 10 to the fourth. This would be 3 significant figures. This would be 4 significant figures. This would be 5 significant figures. They all represent 10,100. And there's no way to show this significance without using scientific notation, because I can't put I could put a decimal point here and that would make it 5 significant figures, but I can't put anything here because it would change the meaning of the word. So sometimes putting things in scientific notation are the best way of representing, being more exact about significant figures and accuracy. Okay, let's see if we got any other ones we could do here. 4.65 times 10 to the ninth, which would be 465. 0, 0, 0, 0, 0, 0. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So, I could write it as this, but I could write it in more compact notation using scientific notation, and if I just had 4.65, then I would know that it's 3 significant figures. Okay, so that's how you determine significant figures. Now in our lab, we're going to take some measurements and look at the accuracy of the measurements that we're going to use. And from that, you could come up with a significant figure. But like I said, we're not going to worry about where. We're just going to look at the number given to us in the problem. We're not worried about how the number of significant figures were determined and what kind of measurement technique. We're going to assume the measurement technique is not something we have to worry about. Okay, now the question is, once you have determined the number of significant figures from a given information, so you do a calculation where you have to multiply, subtract, add, subtract, multiply, and divide. How do the significant figures of the components of the arithmetic operations affect the significant figures that you can put in your answer. You know, the whole thing about, what's the weakest link in something. If you have three numbers multiplied together, but one of the numbers has poor accuracy, then the answer is not going to be good. It's going to be poor accuracy. It's going to be dependent upon that one poorly accurate measurement. So let's look at addition and subtraction. There are rules for addition and subtraction, because subtraction is just the same as addition, except you're adding the additive inverse. Okay, so what you have to do with addition and subtraction is you have to see what is the least accurate decimal location. So what I mean about that is, the ones place, the tenths place, the hundredths place. And you use that least accurate decimal location to set the accuracy of the final answer. So the least accurate decimal location sets the most significant decimal in the answer. I think the best way to do this is just by doing some examples. So let's say we take 1.0, which this has two significant figures, and we're going to add 0.1079. So that one has four significant figures, so you may incorrectly assume that the answer has four significant figures. Or you may say the answer has two significant figures. It's not always dependent upon the accuracy of the initial numbers, but what we do is you basically can use your calculator at this point and just do the math. So if you did the math with your calculator, you get 1.1079. But as far as the least accurate decimal, it's this one right here. It's set by this number, so it's saying the tenths place. So we can't have accuracy beyond the tenths place, so this extra stuff here doesn't count. We can only add this tenths with that tenths to get the final answer. So the answer to this would be 1.1, not 1.1079. So the final answer is two significant figures, and it's limited by that particular place. Okay, so let's do another one here. Let's say 2.37. So that's three significant figures. We'll add 1.974. Again, the decimal or the digit is going to be defined by this one. This is the hundredths place. We don't have accuracy in the thousandths place. So it means that we can really only consider this. Now, the easiest thing to do is just to plug the original two numbers into your calculator. 2.37 plus 1.7974. And what you would get, just from a calculator standpoint, is 4.345, but that one doesn't count. And I must have done something wrong here. Oh, I did the calculator. Well, my finger pushed the wrong button. It's actually 4 here. So this thousandths place doesn't count. Now, if we end up, we can still use rounding. So I'll do that in the next one. But the answer here would be 4.34, which would be three significant figures. 1, 2, 3, 4. 1, 2, 3. Okay, let's do another one. So let's say you have 975, and you add 23.7. Okay, so you just, again, plug in your calculator, and your calculator would say that it's 998.7, but again, this only goes out to the ones place. So the ones is the one that's limiting us. So our answer has to be only accurate to the ones, but we will round that up. So the answer would be 998. So you can use rounding for that one digit that is not significant, because what you would do is you would round that up to 24, and then when you round that to 24, you'd get 999. Okay, let's do 12,000 plus 21. So this one only has two significant figures, and it's only significant to the thousands place. We don't know if these are significant or not. If we put a decimal point, then we would have significance. So we'll do that one next, but let's do this one. So you can see if I add these together, I'll get 12,021, but I'm only accurate to this point, so I would round it off to 12,000. This adding the 21 doesn't change this value at all. This one was two significant figures. This is still two significant figures. Now if I did 12,000 point plus 21, I get 12,021. So this is five significant figures. This is two significant figures. The answer is five significant figures, because this number is accurate to the ones place. This one's accurate to the ones place. Therefore, the answer is accurate to the ones place. Now let's say I had 1.20 times 10 to the fourth plus 21. So we have something in scientific notation and it's something in non-scientific notation. So what you have to do here is you have to rewrite this in non-scientific notation. So I would rewrite this as 12,000 again. But I'd have to remember that this is, because of this zero, I'm accurate to the hundredths place. Is that right? So I'd add these together. I'd still get 12,021. But again, this 21 wouldn't count. So what I would do is I would rewrite this back as in scientific notation to get the right answer. Because if I just wrote it as 12,000, then I'd lose this significance of this one extra digit. So it's a little tricky there under those circumstances. Okay, so that is that's addition. If you're in scientific notation, convert it to non-scientific notation. Do the addition, making sure you pay attention to which is the most, the least accurate digit. I guess, yeah. If you don't have it in scientific notation and you don't have a decimal point, then you have to assume that it's just based upon the number of non-zero characters. Okay, then we have multiplication. And division. And it's the same rule for both of these. But for this, the answer has the number of significant figures of the part of the calculation with the least significant figures. Okay. So we don't, if this is in scientific notation, we don't have to worry about converting anything. But let's deal with cases where you don't have scientific notation. So let's say you have 2.2 times 4.35. Okay, so you can use your calculator for this. 2.2 times 4.35. And I'll get 9.57. So let's look at the significant figures of the beginning calculation. This has 2 significant figures. This one has 3 significant figures. The one that has the least number of significant figures of the product is 2 significant figures. So this will be rounded up to 9.6. Has 2 significant figures. These are going to be the same. You can't get more significant figures. You can only have the number of significant figures associated with the part of the product. And if you had more than 2 things, if you multiply 3 things together, you'd use the one with the least. Okay, let's say you had 2.20 times 4.35. You'd still get 9.57, but the answer would be 9.57 because this has 3 significant figures. This has 3 significant figures. Therefore, the answer has 3 significant figures. Okay, let's do 12,100 times 4.975. Okay, so let's stick that in our calculator. 12,100 times 4.975. And I would get 60,197.5. But this has 3 significant figures because these 2 are not significant. They're just placeholders. This one has 4 significant figures. Therefore, the answer has to have, I almost got it wrong there, 3 significant figures. So how would you write that? Well, you could write it as 60,200. I would round this up to 200 because I only have 3 significant figures. You could do it as 6.02 times 10 to the 4th. That would also work. Now if I had 12,000, or if I had 1.210 times 10 to the 4th, which is the same as this number, except I've added 1 significant figure, and you multiply by 4.975, again, you can plug those in your calculator. You don't have to convert with multiplication and division. You don't have to change that. You can just use your scientific notation on your calculator. So I'll put 1.120. You don't even have to put the 0 in there. E to the 4th and multiply by 4.975, and you're going to get the same answer. Why didn't I get the same answer? It's because I did it wrong. 1.21, I did 1.12. Okay, so you get the same answer. 6197.5. So this has 4 significant figures. 1, 2, 3, 4. This one has 4 significant figures. So the answer is going to be 4 significant figures. So it's going to be 60,001. Well, interestingly, if you rounded that up, you'd round it up to 200. The problem is, how do you show 4 significant figures? Well, you can't here. You would have to do it as 6.020 times 10 to the 4th. You really couldn't show the appropriate number of significant figures without using scientific notation. Now, if this had rounded down to 1.617, 6019, say, then you wouldn't have to put it in scientific notation. But in this case, I would have to put it in scientific notation to get the number with the correct number of significant figures. Okay, now let's do division. So division is the same kind of thing. If you had 3.45 divided by 7, let's do 7.2. So you plug that in your calculator. 3.45 divided by 7.2. You know, you get a whole bunch of numbers here. 0.4791666666. Okay. This has 3 significant figures. This has 2 significant figures. Therefore, the answer has to be 2 significant figures. Two significant figures. So you take this and you would make it into 2 significant figures. So you have 7, 9 to 3 significant figures. So you'd round that up to 0.48. Or you could do 4.8 times 10 to the minus 1. Either one of those would be fine. Now if I had an additional, if I had a 0 here, that would make it 3 significant figures, and then the answer would be 0.479. Okay, let's do 7,450,000 divided by 761.2. Okay, so how many significant figures? Well, this one only has 3 because these zeros are not significant. If I wanted to show more significance, I'd have to do it in scientific notation. This one has 4 significant figures. So the least of these two is going to be 3. And then all we have to do is just plug into our our calculator would say 9787.17814. So we need 3 significant figures. So the way we would do that is, again, this one's going to be a little tricky because if I round this up, well, no, that'll be fine. So this one becomes 9790. So what I've done is I've rounded 87 up to 90. So I have 3 significant figures. This 0 is not significant. If this had gotten rounded up to 9800, then I'd have to rewrite it in scientific notation. So let's write this 9.79 times 10 to the third. That would be another way of writing it. Notice I'm not adding the 0 here because that's not significant. Okay, so what I'm going to ask you to do is I'm going to ask you to do this handout. And I'll have you hand it in. So I want you to upload this before Friday. So what is it? In-class handouts. So go ahead, you can download this to your computer and then put your answers on a separate sheet of paper. You can print it out and then you're going to upload it to this, and I'm going to put a due date on it of Friday. So make sure you have this done. So I'll show you how this works. So you can see I've set it up as a file upload, and I'll come down here and I'll say it's due Friday. And we can put a time. So we're going to put it at 8 9, just before class, 9:30 a.m. Okay, save. Now as far as any, let's see if I can change this to some percentage drop with respect to time. There should be some way of doing that. Oh, add, I think I can do it here. Maybe not. There should be some way of doing it. Oh well, I'll fix it. So I'm going to put some kind of penalty on it if you turn it in late. So let me just show you what the assignment looks like. Okay, so save that. No, I don't need to get rid of that. So assign to everybody. Let's go back. Look at the assignment. Okay. So we're going to open this up. So open it with Adobe Reader. So basically, all you have to do is you're given certain operations, addition, and you can put your answers here. So if you're doing it on a separate piece of paper, just write down 1.3 plus 0.25. For example, this one, I'll give you the first one. This has two significant figures. This has two significant figures, but this is addition, so it's only accurate to the tenths place. So when you add this together, you'll get 1.55, which you will round up and make into 1.6. Okay, so that's how that works. Here, there's some ones with that are in scientific notation, so you'll want to convert those to non-scientific notation, but paying attention to where the least or the most accurate digit is, and then doing that appropriately. So these are all addition and subtraction. Then when you get to multiplication and division, those are pretty easy. The only one you have to be careful about here is 3120. So this one only has 3 significant figures, not 5 significant figures. This one has 3 significant figures because of the 0, which we didn't talk about, so I'll talk about that in a second. Let's see if there's any others here. This one only has 3 significant figures. Okay, so go ahead and have those ready by Friday. If you have any questions, let me know. I'm not going to post the answers. Just want you to do it. You'll get most of them right. And if you have questions, we can go over specific ones on Friday if you're still confused. Let's go back here to this. So the one thing that you can see in that problem is if you have 0.0125. So how many significant figures is this if you were doing this multiplication problem? So you have this times 137 or 1,374 multiplication. You might say this is 4 significant figures, but when you're to the right of the decimal point, these zeros before you get to the first non-zero number are placeholders. So this only has 3 significant figures. And this one would have 4 significant figures. So the answer is going to be 3 significant figures, the smaller of these two. So let's go ahead and plug that in. So 0.0125 times 1,374. I think I accidentally put a dot there. Okay. So the answer I get is 17.175. But we're only doing 3 significant figures, so this would be written as 17.2. So that's how you deal with zeros in this direction that are just to the right. So, 0.00005, that's one significant figure. These 4 zeros are here so that it puts this 5 in the appropriate place in terms of a decimal. So these are not significant, just like 50,000 on the other side. These are not significant. But if you do have numbers here, these are significant. Okay, so that's your instruction on significant figures. We've talked about, part of the significant figures is we talked about scientific notation. So I guess there's 2 kinds of scientific notation. The one that I'm more used to is where you have numbers between 1 and 10, and then add something to the times 10 to some power. So you might have 1.3 times 10 to the 4th. You might have 7.9 times 10 to the 3rd. You would tend to put them in this form because you can more readily see how many significant figures the number has. I think there are cases where somebody would do 19.7 times 10 to the 3rd. So there is a number that's not between 1 and 10 here. I'm trying to remember when that's done. I guess if you were talking about, multiples of, like, if you wanted to do this so that it was always 10 to the 3rd, 10 to the 6th, 10 to the 9th, so that you have kilo, mega, whatever the next one is, not nano, but mega. I forget what the next one is. Giga, right? Megabytes, gigabytes, terabytes. So yeah, I think sometimes you could do it like this. So you might have, instead of 1.97 times 10 to the 4th, you might write it as 19.7 times 10 to the 3rd. Say it was meters, so that would be 19.7 kilometers. Or if you did it as like a resistance, we'll talk about resistance at some point, but if you had a really big resistance, like 545,000 ohms, you could write that as 5.45 times 10 to the 5th ohms. Or you could write it as 445 times 10 to the 3rd ohms. And the reason you would do that is because this would be changed into a kilo. So you'd have 545 kilo ohms. K ohms. So that's probably the only time that you wouldn't just use numbers between 1 and 10 to write them in scientific notation, is if for some reason you're wanting to write the magnitude of something in terms of kilo, mega, giga, tera, so forth. Okay, so that is the material in Chapter 1. The homework covers a few little extra things, but you can just watch. You can watch the video. There's a few things about estimation, um, but just look at the example. So we're almost an hour and 10 minutes here. So let me just use the last few minutes here to talk about where we're going. The next section is we're going to talk about one-dimensional motion. So what we're going to do is we're going to introduce displacement, velocity, acceleration. So displacement, as I think we mentioned earlier, has units of meters. Velocity has meters per second. Might have mentioned this in calculus. Acceleration is meters per second squared. And these are the main three variables when you talk about things moving, whether they're molecules, whether they're cars, spacecraft, planets, to describe where something is and how fast it's moving and how quickly it's changing its velocity. Use these three quantities. And then we're going to concentrate on two special cases, which is constant velocity So in constant velocity situations, displacement changes, but the velocity doesn't change, and the acceleration is zero. So this is kind of like something driving along the road at a constant speed. You know, how do you calculate how far something goes in a certain amount of time? The next thing that we'll talk about, which is we'll spend most of the time, is constant acceleration. And what constant acceleration does is it's a hard enough problem that you can do some interesting things, but it's not so difficult. And we'll come up with we'll come up with equations of motion for constant acceleration. And you know, where does constant acceleration happen? Well, if you drop something and it falls under gravity, so we call that free fall. That has constant acceleration of whatever the acceleration due to gravity is, which is going to be dependent on which planet you are and where you are on the planet relative to the center. And also, if you can model things where you push something along a surface without friction most of the time, assuming it's without, well, that's probably not a necessary requirement, but if you push it with a constant force, you'll get a constant acceleration. Now, we don't talk about forces until the fourth chapter in this book, but this allows us to introduce the whole concept of how do you solve physics problems. So it's going to, part of this is going to be physics. How do you relate these three variables when the acceleration is constant? But also just how do you work through physics problems involving significant figures? Just how do you think about getting from given the information to getting the answer? So that'll be the second chapter, and we'll spend a fair amount of time on problem solving. Okay, so that's it. Remember, this is your Wednesday assignments. Again, if you want to, I kind of have an idea who's going to be. Michaela and Ethan are probably going to be partners. Whether Eric and Mason want to work together, they may not want to. So you guys can decide. But let me know if you've got them. Otherwise, I'll just assign them when you get to class. Remember, you need to be there before 8 o'clock, or the doors may or will close. Bring your computer. If you are having Governor's School computer and you want to use that to work on your Arduino stuff, if you have a home computer, you can just do it without any problem. We probably won't start the Arduino stuff until everybody's got their equipment, so you can look at it and play around with it a little bit, but probably won't start assigning anything until at least the second week after the second Wednesday, so we're all together. But I will hand them out. that first week, and you'll be able to take that home with you. Make sure you bring a mask. I don't want to die, so I've got things going against me. Tall people, type A blood type. I think we're going to be pretty safe. Let me know if you have any questions.